Buried deep inside a mountain range, fighter jets sit hidden behind hundreds of meters of solid rock. No satellite can see them, no missile can easily reach them. This is Eagle 44, Iran's underground airbase designed to survive modern war. Welcome to the Survival Bunker, where we study the brutal reality of surviving war zones, sieges, and battlefield collapse. Today, we are not analyzing a battlefield tactic or a field expedient survival solution. We are going underground, into a mountain. Eagle 44 is Iran's operational underground airbase, publicly revealed by the Islamic Revolutionary Guard Corps Air Force in February 2023. It is not a concept or a prototype. It is a functioning military installation, housing combat aircraft inside a carved-out mountain, engineered to absorb precision strikes, defeat satellite surveillance, and launch offensive air operations from a position that conventional targeting doctrine cannot easily reach. This is how you build an airbase that survives modern war. Why hide an airbase under a mountain? To understand why Eagle 44 exists, you have to understand what happened to exposed airfields in modern conflicts. The 1991 Gulf War established the template. Coalition air planners targeted Iraqi airfields in the opening hours of the campaign with precision-guided munitions designed specifically to crater runways and destroy parked aircraft. Iraqi jets that survived the initial strikes had nowhere to take off from. The airfield itself, the paved surface, the fuel lines, the above-ground hangars, was the vulnerability. Destroy the infrastructure and the aircraft become irrelevant regardless of their condition. That lesson was observed, documented, and studied by every military that considered itself a potential target of US or Israeli air power in the decades that followed. The Iranian military drew a direct operational conclusion. A traditional airbase is a target, not an asset. The moment its location is known, and in the age of commercial satellite imagery, every major airfield's location is known. It can be struck, its runways can be cratered, and its aircraft can be destroyed on the ground before they ever fly. The survivability problem is not primarily about air defense systems. Surface-to-air missile batteries can be destroyed, jammed, or saturated. The problem is architectural. If the aircraft and the infrastructure that supports them are visible and accessible, they are vulnerable. The engineering solution Eagle 44 represents is not new in principle. It is the oldest defensive logic in existence applied to 21st century air power. Put it underground, put rock above it, and make it structurally impossible to reach with anything short of direct penetration. The location advantage, right? The Zagros Mountains. Eagle 44's position within the Zagros mountain range in western Iran is, well, not incidental. It's actually the first line of its defense system. The Zagros range stretches for about 1,500 kilometers through western and southwestern Iran, with peak elevations going over 4,000 meters. The geology here is mostly folded sedimentary rock, limestone and dolomite layers that have been compressed into tight anticlines over millions of years of tectonic activity. Now, this geology has two properties that are absolutely critical to underground base engineering. First, it's hard enough to be structurally stable when tunneled, and second, it exists in enough depth and thickness to absorb the overpressure effects of surface or near-surface detonations, without transmitting lethal shockwaves to underground spaces at operational depth. The terrain itself, actually provides concealment in ways that installations on flat terrain just can't replicate. The rugged topography of the Zagros creates radar ground clutter that makes low-altitude surveillance much more complicated, offers natural visual screening from ground observation, and restricts the approach corridors available to attacking aircraft. Access roads to mountain installations are, well, narrow, switchbacked, and pretty easy to defend. A convoy heading toward an underground base entrance in the Zagros is visible for only a fraction of the distance it would be on open terrain, and it's funneled into just a few approach routes that can be covered by relatively small defensive elements. The mountain is not just a hiding place. It is, a force multiplier for every defensive system associated with the installation. The structure of Eagle 44. The IRGC Air Force's February 2023 public reveal of Eagle 44, released through Iranian state media and including interior footage, provided the first confirmed visual documentation of the base's internal architecture. That footage, analyzed alongside open-source satellite imagery and statements from Iranian military officials, allows a structural reconstruction of the installation's key design elements. The base is accessed through large tunnel entrances carved directly into mountain rock faces wide enough to accommodate combat aircraft movement. The entrance geometry is critical. Tunnel openings must be large enough to permit aircraft ingress and egress without damage to airframe components, but their orientation relative to prevailing surveillance angles determines how much of the interior is visible from external observation points. Eagle 44's entrance configurations, based on released imagery, are oriented to minimize direct line of sight from overhead satellite passes. Inside, the base consists of these extended tunnel corridors, connecting individual hardened hangar chambers carved right into the rock. Each hangar is sized to accommodate specific aircraft types. The revealed footage showed aircraft identified as F-4 Phantom variants and, interestingly, what appeared to be domestically modified fighter types. The hangar chambers are reinforced with concrete lining applied to the tunnel walls and ceilings, which provides structural stability and helps reduce spalling risk from nearby detonations. Multiple entry and exit points distribute operational traffic and, crucially, prevent a single entrance blockage from immobilizing the entire installation. This redundant access architecture is, honestly, a standard design requirement for underground military facilities. A base with a single entrance is basically a trap if that entrance is destroyed or sealed. The survivability case for Eagle 44 rests, really, on the physics of overpressure dissipation through rock mass. When a munition detonates at or near the surface above an underground space, it generates a pressure wave that propagates through the surrounding rock. The intensity of that pressure wave, measured in pounds per square inch or pascals, decreases as the inverse square of distance from the detonation point. At sufficient depth, the overpressure arriving at an underground chamber falls below the structural failure threshold of the reinforced concrete lining and the rock itself. The critical variable is depth of burial. Modern bunker-busting munitions, the US GBU-57 massive ordnance penetrator, for example, are designed to penetrate hardened earth and concrete before detonating, extending the effective overpressure depth. The GBU-57 is credited with a penetration capability of approximately 60 meters in concrete before detonation. Against solid rock, penetration depth is significantly reduced because rock is denser and harder than concrete. An underground facility at operational depth within a solid rock mountain requires penetrating the mountain itself, not merely the soil and concrete cover of a surface bunker. Eagle 44's tunnel design adds a second layer of blast protection through geometry. Straight tunnels transmit blast pressure efficiently along their length. A detonation at one end sends an overpressure wave directly to the other. Curved and branching tunnel systems disperse and dissipate that pressure wave at each change in direction, reducing the peak pressure arriving at any individual chamber. The revealed footage of Eagle 44 shows tunnel corridors with deliberate curvature, consistent with blast-mitigating tunnel design rather than the straight-line geometry that would be, well, simpler to construct. Reinforced blast doors at tunnel intersections provide a final mechanical barrier against overpressure transmission. Closed blast doors interrupt the pressure wave's path through the tunnel network, protecting sections of the base beyond the door from the effects of a detonation in the section before it. Moving jets underground. Operating fixed-wing combat aircraft inside a mountain introduces engineering constraints that really have no equivalent in conventional airbase design. The primary challenge is clearance geometry. A fighter aircraft's wingspan, the F-4 Phantoms is approximately 11.7 meters, defines the minimum tunnel width required for aircraft movement. Add ground handling equipment, safety clearance margins, and the need for maintenance personnel to work alongside the aircraft, and the tunnel cross-section expands significantly. Tunnel construction at that scale in solid rock requires sustained heavy boring and blasting operations, generating surface signatures that surveillance systems can detect. The construction phase of a facility like Eagle 44 is its period of maximum vulnerability. Aircraft movement inside the tunnel system requires guided ground handling rather than the self-powered taxi operations normal at surface airfields. Jet engines produce exhaust at temperatures and volumes that would make enclosed tunnel operation without massive ventilation infrastructure immediately hazardous to personnel and equipment. Aircraft are moved through the tunnels using ground tow vehicles along marked corridors with controlled lighting. The tunnel walls carry markings for clearance verification. Ventilation is the most technically demanding continuous operational requirement. Jet fuel combustion, engine testing, vehicle exhausts, and the metabolic output of a large underground workforce all generate atmospheric contamination that must be continuously extracted and replaced. Eagle 44's ventilation system, the details of which have not been publicly disclosed, represents one of the installation's critical infrastructure dependencies. Disruption of ventilation in a sealed underground space creates a survivability crisis for personnel, faster than almost any other system failure. Running a functional combat airbase without access to sunlight, open air, or, the logistical convenience of surface operations requires solving a layered set of infrastructure problems all at once. Fuel storage and handling inside a rock tunnel is an acute fire risk. Jet fuel in enclosed spaces produces vapors that, at the right concentration, are explosively flammable. Eagle 44's fuel infrastructure must include sealed storage tanks, vapor containment systems, and fuel transfer equipment that is engineered to eliminate ignition sources. Fire suppression systems throughout the fuel handling zones are not optional. A fuel fire inside an enclosed tunnel system can propagate faster than personnel can evacuate. Weapon storage and handling introduces a parallel requirement. Ordnance awaiting loading onto aircraft must be stored at safe separations from fuel systems, maintained within temperature and humidity parameters that preserve reliability, and moved through the tunnel system without impact or electrical discharge risks. The logistics of arming aircraft for a combat sortie in a surface hangar are complex. The same operation in a rock tunnel with constrained space and, honestly, limited equipment access is significantly more demanding. Power infrastructure, lighting, ventilation fans, communication systems, maintenance equipment, fuel pumps, requires either grid connection with hardened underground cable routing or on-site generation with associated fuel storage for generators. A loss of power in an underground base is not just an inconvenience, it is a life safety event. Defense against modern warfare. Eagle 44's defensive architecture addresses three distinct threat categories. Against satellite surveillance, the base presents minimal surface signature during non-operational periods. Aircraft are stored inside the mountain. Support vehicles and personnel move through covered access routes. The entrances, when closed, are visually consistent with natural rock faces from overhead observation angles. Commercial satellite imagery of the Zagros region identified tunnel entrance signatures consistent with Eagle 44's location before the IRGC's 2023 reveal. But the internal state and operational capacity of the facility were not determinable from surface observation alone. Against precision-guided missiles, the rock mass above the operational chambers provides shielding that no surface hardening can replicate at equivalent cost. A bunker-busting munition that penetrates 60 meters of concrete must penetrate a proportionally greater depth of denser solid rock to reach the same overpressure effect at the target chamber. Multiple simultaneous strikes on different points of the mountain's surface face the same attenuation problem independently at each impact point. Against airstrikes targeting parked aircraft, Eagle 44 presents no target. Aircraft inside the mountain are not visible from the air and are not reachable by weapons that cannot first penetrate the mountain above them. The moment an aircraft exits the tunnel onto a surface dispersal area, it becomes visible and targetable, but that exposure window is measured in minutes rather than the continuous exposure of a parked aircraft at a conventional airfield. Limitations. Eagle 44 is not invulnerable. Its limitations are structural and cannot be engineered away. Entrance points are the decisive vulnerability. A tunnel entrance that is sealed by a precision strike collapsing the rock face above it, by a large yield detonation at the entrance itself, or by physical obstruction, traps everything inside. Aircraft that cannot exit cannot fly. Personnel who cannot exit are casualties. The multiple entrance design mitigates this risk but does not eliminate it. A sufficiently resourced attack on all entrance points simultaneously could seal the installation. Exit bottlenecks limit the rate at which the base can generate combat sorties. A conventional airfield can launch aircraft from multiple runway thresholds simultaneously. An underground base with limited tunnel exits can only clear one aircraft at a time through each exit corridor. In a time-critical launch scenario, this throughput constraint is operationally significant. Coordination complexity inside an underground installation is substantially higher than at a surface base. Communications, aircraft movement sequencing, fuel and weapons coordination, and emergency response all operate in an environment where the consequences of error are amplified by the enclosed space and limited exit options. Why this still matters today. Eagle 44 is not a uniquely Iranian development. Underground military basing is experiencing a global renaissance driven by the same threat calculus that produced the Zagros installation. North Korea has operated the most extensive underground military infrastructure in the world for decades. Tunneled artillery positions, underground naval bases, and deeply buried command facilities that have absorbed decades of international pressure without meaningful external assessment of their contents. China's People's Liberation Army has invested substantially in underground facilities for both nuclear forces and conventional military equipment, with tunnel networks in multiple military regions assessed by analysts as housing significant stored capability. NATO members, including Norway and Sweden, maintain mountain-based military facilities drawing on the same geological logic as Eagle 44. The trend, really reflects a doctrinal shift. In an era of persistent surveillance and precision strike, survivability, it requires concealment. And concealment at scale, honestly, demands going underground. Surface hardening, after all, has physical limits. Rock depth does not. The bigger lesson here is pretty clear. Eagle 44 encodes a principle that has governed military survival engineering across every era of warfare. The most durable defense is the one that removes the asset from the threat environment entirely. Armor, for example, protects a tank from direct fire but keeps it in the threat environment. Air defense missiles can protect an airfield from attack, but keep the airfield visible and targetable. A mountain, though, puts the aircraft beyond the reach of everything except the most specialized penetrating munitions, operated at significant cost and risk, against a target whose precise internal configuration remains unknown to the attacker. The rock is not a weapon. It is, in fact, the absence of vulnerability. Eagle 44 is not some curiosity or a propaganda display. It is a documented engineering response to a documented threat. Precision air power that has demonstrated in Iraq, in Libya, and in Syria that surface airfields simply do not survive determined attack. The Iranians looked at that record and, well, put their jets inside a mountain, the oldest defensive instinct in military history applied to 21st century air power. The mountain, frankly, does not care what generation your munitions are. If this briefing changed how you think about modern military survivability and underground warfare engineering, subscribe to the Survival Bunker and share this video. Every share, honestly, puts this research in front of someone who takes real-world military history seriously. Hit the notification bell, and we will see you at the next briefing.